पानी पानी भी नहीं। Electromagnetism ग्रेजुएट लेवल मैसिव ग्रेजुएट लेवल में सब बोल सकता हूँ राइट टू एक्सट्रैक्ट क्लास अंडर ग्रेजुएट आई डोंट इवन ट्राई टू आस्क अभी प्लास्टिक खराब है चिपक रहा है
शायद ऐसा ही होना चाहिए लेकिन पहले भी ऐसा ही Hello?
Hello?
Good. How was your office hours? Do students show up?
No. No, they never showed up before the online adjustments anyway.
I see. Yeah.
I didn't expect them to. Just gotta still make myself
Did the
available.
lab courses, right? I mean, usually they don't have much.
Right.
And you anyway meet for 1 or 2 hours too, right? In the lab, at least during the lab. But now you would expect that they have more questions because it's a recorded thing. One would think that there's this confusion, that confusion. Well, true. Are you working on your master's? Like you have to finish your master's, correct? Did you say it is in the summer?
Yeah, it's this summer. I should be wrapping up.
Okay. And did you hear anything from Michigan yet?
No, I'm just about done. The only thing I'm missing is the recommendation letters. I've got 2 of them in now. I'm still waiting on a 3rd one. Thank you so much, by the way, for being so quick about yours. It's getting other people to do them is getting, I don't know, can be a pain.
Yeah.
That's happening.
Yeah, I can. Sometimes I also delay it. I mean, it's just, yeah, I mean, prioritizing. I think it's easy to say that, okay, I'll do this later, kind of.
Yeah. Every time I've applied to a graduate school, that's what I've had this issue of trying to get recommendations turned in.
But don't hesitate to ask people. I think they don't usually do. I mean, if you ask it politely, they don't really mind. In fact, it helps. So, okay, there's a reminder. Otherwise, it's easy to forget. At least it happens with me, right? Once it goes below in the things to do list, and you see it every day, so you forget that this is to be done and there's a deadline. So it's good to remind. Yeah.
How are the undergraduates adjusting in your courses to the online stuff? Y'all doing all right?
Tell that again. I think
Like the
a little
students.
distant. You sound a little distant.
Oh, okay.
Yeah, now it's good.
Yeah, could be I was just sitting back further, maybe.
Yeah, now it's good. Yeah.
Okay. The students in your undergraduate course, how are they managing okay in the transition here?
I'm not in touch with everyone, but those who are in my classes, they all look okay. They are all tired of staying at home. Yeah, I mean, they show it out. I think you seem to be the only person who has no. I think you've almost said, "Oh, there's not much difference," right?
Exactly, no difference. I'm fine with it.
Yeah. So, but I think others do miss coming to the university.
Right.
In fact, there was a proposition made yesterday in the other class that maybe they were wondering if it is possible to have a physics launch so
Physics.
that they can come and hang out online, at least chat.
Oh, physics. Oh, like an online lunch together?
Yeah, online launch. Like we used to have this coffee room there in the right next to my room actually. So the
I see.
proposition was that, is it possible to have it on Zoom so that students can come all there, and if anyone is there, they can chat.
Oh, so it's like a lounge that's like a meeting on Zoom that runs continuously or something? Like,
Yes, exactly.
I see.
Yeah, and no one is in charge. You just come and no
Right.
agenda. You just come and say hello and go.
I see.
Or if you want, you can talk also. Yeah,
Right.
but there's no requirement for anyone to talk to. So it seems like that was a interesting suggestion. So I put it forward to the chair and Bob, and Bob is working on it. Oh, sure. I think Angela is here. Maybe she was waiting. Hello,
Hi.
Angela. Yes.
Yeah, I'm here. Yeah.
Okay. How are you?
I'm good. I'm okay.
Yeah. Normal now?
Yeah, much better.
Okay. Much better still. It's not normal.
Yeah, pretty normal actually.
Okay. Yeah. Yeah, I was just telling Justin about the suggestion made in the other class that maybe a students launch kind of concept might be helpful.
Yeah.
So I think it might be possible. The only catch is how do you set it up in Zoom that is always functioning, something like that. So, have you guys heard of Slack?
I've heard of it. I've never used it. I've heard of it.
Yeah, we kind of used it a little bit for the Women in STEM Confluence, but it never worked. I mean, we started using it for that. But yeah.
Women in STEM conference. I see. This is the one that is coming up on 20th.
That was supposed to come up, but it got cancelled.
Okay, so it is not going to be even held online on Zoom or anything.
Oh no! I don't think we made any plans to make it Zoom online.
I see. Yeah. Okay. Yeah, that was one suggestion made that maybe instead of Zoom, maybe Slack might be an option, but I don't know. Yeah. Oh, so we have you on video. So,
Yeah.
Yeah.
Kind of become so gone.
Okay. Okay. So let's. So, okay. Before anything, is there anything to say about homework or anything? There is a homework due that is on 21st on Tuesday, correct? Let me look it up. I almost forgot about this course until half an hour back. That there is a class. I was almost planning to leave. We were thinking of okay, and then this one struck me. Okay, so okay. Oh, this is not even written here. Homework 7. It's due April 21st. That's Tuesday, I suppose. And final exam will be like our midterm 3. This will take home. That's May 6th, which is a Wednesday. And the time doesn't really matter because it's going to be take home. Let's see. Yeah, Wednesday. It's supposed to be at 10:15, but who cares? Yeah. Okay. Yeah, so we did dynamics. We introduced time into the what happens when things are moving, and we talked about uniform velocity, and we derived the potentials. And the immediate thing to do is to take the derivatives and calculate the electric and magnetic field, but I'm going to skip that whole part. Okay, so it's a pretty it's just taking the derivatives and interpreting it. And there is one nice thing that one can do is take some limits and see what happens, but I'm going to skip that. I gave you a diagrammatic picture of how the electric field and magnetic field looks like in different frames. It's good to appreciate that this transformation of electric field and magnetic field, or the expression for electric field and magnetic fields from a moving frame of a point charge, was written down all the way back in 1875. Remember, 1865 is when Maxwell gave his equations. Right afterwards, within 10 years or 15 years, it was written down first by Heaviside. But the difference is that they did not, or even contemporaries after that, Lawrence, Poincaré, everyone, they all had these expressions, which is very relativistic, very much like what Einstein had in his hands, but they did not make the right interpretation that these are all transformation of the same things from going from one frame to the other. Like if you are in a rest frame, whatever you have, make a transformation, you get these results. That was not as profoundly made as Einstein did, and that was the big contribution from Einstein. That he not only said it is in this context, he changed the context altogether and said this is anything whenever something has a finite speed, or any signal has a finite speed, then these kind of counterintuitive effects will be available. And that was the contribution in that. So we want to keep going with the time. What else can you work on when you have time involved? And this is broadly called radiation. So this will be radiation fields, let's say. Like just radiation. Let's again write down the equation just for the sake of it. So we have del dot E is equal to rho over epsilon naught, and del cross E plus the time rate of change of magnetic field is equal to 0. The magnetic field del dotted with B is equal to 0, and del crossed with B over mu naught, which can be written as mu naught epsilon naught dE by dt plus mu naught J. Right. Often I write the mu naught on the left hand side, but that's perfectly okay. Okay, and this can be written as a wave equation. We showed that all this corresponds to, if you were to write it in terms of, let me also write that. So magnetic field can be written in terms of a vector potential, pretty much an implication from the second Maxwell's equation, or the divergence of the magnetic field going to 0. And the electric field is the negative gradient of phi. That's what would have happened in statics, but now the dynamics involves this extra term, right? That's the major contribution. If you want, that is the momentum also contributes to the electric field, not just the energy or the electric potential. And we showed that the electric potential and the magnetic potential satisfy the wave equation wherever in a region where there is no charges. So that's your 1 over rho. And the same thing for vector potential. Okay, all nice. So this is the construction of the problem, and we found the solution for this scalar potential and vector potential, and that was the difference from the static scenario, and that was the following. That's what we want to do today, but for a general time motion. So this is 1 over 4 pi epsilon naught. So we can have integral over d cube r prime. I have to squeeze the whole expression in, so I'm going to write small. So let me know if it is not readable. Okay, so there's a time integral dt prime minus infinity to plus infinity, and the Green's function had a delta function, which is t minus t prime minus 1 over c times r minus r prime, or that's 1 over c. Right? That's rho prime t prime. Right, this integral over t and the delta function, if it did not exist, then you're in statics. This is your modification if you want. And a similarly, let me leave a little space there. There's one thing we can immediately do, and that's how we will work here. Notice when we were doing it for the point charge moving with a uniform velocity, we use the fact that integral of dr can be performed because the charge existed only on one point in space. But this time we will do the opposite. Let me do the time integral because there is no t prime anywhere else. I can do this time integral at this stage, and that is equal to 1 over 4 pi epsilon naught d cube r prime. Right. When I do the t prime integral, t prime has to be replaced with t minus that quantity, and that's the only difference. So rho of r prime, comma, t minus so notice how the time has been retarded. If speed of light was infinity, this term would be 0, and it is equivalent to static problem with the current or the source moving with time. Nothing changes. You just correct your position of the charge accordingly, and everything is like statics. But if not, there is this additional feature in there, right? That's the finite speed of the signal coming into picture. So this is the extra term, and this whole thing is called the retarded time. Same thing for vector field or vector potential, sorry. It's equal to mu naught over 4 pi and this is j and time is retarded. That's the only difference. Okay. And now we want to keep this very general, and we want to talk about the following scenario. Remember, R prime is the position of sources, and R is the position of the observation point. So let's have the following scenario. So this is what is called the radiation regime. Right, so let's say R prime. So there is some sources here. So this is R prime. We are integrating over R prime, remember, so that you can capture all the charges that's there. It could be extended to quite a big extent, but everything is confined in a region. And let's say you're making an observation which is very far. So that's your R. That's your observation point. Okay, so these are sources, and that's your observation point. Okay, and think of this could be your sample inside your lab, and that could be the sensor also inside of the lab, but this distance could be very large, right? If the sources are completely away, this could be within a micrometer, and this could be 10 meters away, and that's good enough. That's infinity, right? Micrometer and 1 meter is pretty much infinity. 10 raised to minus 6 as a million times larger. So if you're doing an experiment, it will be in the third, fourth decimal accuracy. It is infinity. In that sense, that's an approximation. Very well, very nice limit. And let's say this distance is, so this distance will be R minus R prime. So let's, so the regime we are going to talk about is R minus R prime is very much large compared to some characteristic frequencies. So, something is happening periodically, let us say. So there is information being given out every certain moment of time. So this is some characteristic time times C, right? Some characteristic time of the sample, because you want a characteristic time of sample. Like if it was something that is periodically happening, there is a unique time associated with it, and you can build that. Or you can say how much time it takes to go from here to there is very large compared to whatever is happening inside inside the sample. Okay, so that's the limit. And what can we do with that? So in that limit, the claim is that this whole expression that we have, so this expression, so this is an exact result for any source, any charge distribution, any current distribution. But it's exact, but it's hardly doable. You cannot work with like even the uniformly moving charge. It was extremely hard. But now the point is, if we make that radiation zone approximation, we can almost do this for any charge. And primarily, the idea would be to think along radio and radio antenna, right? You want to make an antenna which can emit a signal, and there is another radio sitting there absorbing it. So if you're thinking of antenna, pretty much antenna or antenna that emits light, both antenna and receiver is very similar. Okay, so that's a basic idea. And the conclusion will be that anything that is accelerating is going to emit charge. So in that regime, let's see what can we talk about. So R minus R prime, right? So let's say R, so R minus R prime, that's one quantity that is coming in. We want to see how this looks like. So let's say this is square root of R square plus R prime square minus of 2R dotted with R prime. So what kind of approximation is this. So let's pull out an R. So this is equal to 1 over, so I will write the other one first. So this is 1 minus 2 times R hat, because one of the R's cancels out, and then this is dotted with R prime over R, right? And then there is plus R prime over R the whole square. I'm interested only in the leading approximation. Like I don't want second order effects. So in the leading order of this approximation is governed by this first term and not the second term. Like I want only the leading order, no extra. I want the first correction from what we have in statics in a very far field region. So that's governed by this. So we'll delete this altogether. So we are neglecting this. And once this is a square root, I can expand this as 1. There's a square root has a half in it. So this is minus half of 2 times R hat dotted with vector R prime dot vector R plus higher orders. So let me call it order square. Right? So this is the first order. This is the 0th order. That's order square. In what? You can say R prime over R, magnitude of R prime over over R. So that's equal to, you can say this is R, right, minus of vector R, or these two can cancel out. So this is R hat dotted with R prime plus order square. I mean, now this is not really order square, but because now there is a length in the length scale in the problem, so it's plus higher orders. Okay, that's going to be the approximation. In that same approximation, that shows up. So where does this show up? Remember, the retarded time has that, and there is also inside in the denominator. So let me write this down. How does electric potential look like? So electric potential is phi of R comma t is equal to 1 over 4 pi epsilon naught d cube R prime and there is rho of R prime comma t minus, that is the distance R minus R prime over C coming up in the retarded time, but I'm making this approximation that I want only this much. So this will be R over C and minus of R hat dotted with R prime over C. Right, that's the approximation we are making. Okay, clear? And divided by, it's the magnitude of the distance that shows up. I'll keep the same thing. So this is R, or I don't have to write the magnitude because that's the length itself. So it is R minus R hat dotted with R prime. But notice, if I were to expand this, I have already captured the leading order here. Anything of the expansion, this will be a higher order. So I don't even have to keep this. So you can drop this in the denominator. I can drop the next leading order. So I just had to keep R. Okay, is that clear? There was a factor of this here also. But when I invert it, since anyway I'm using expanding it to the next order, when I expand it, that goes away and that's not going to contribute. It is going to be leading a second order. So that's not there. Is that argument clear? Okay. If I proceed, that immediately simplifies. Notice how the things have simplified. This was in the denominator, but now it is r prime independent. So I can bring that out of the integral completely. So suddenly, so the problem has significantly simplified. That's 1 over r outside. And I just have to integrate over the charge density, except that the time and r is inside in there. So it's at a retarded time. So r prime, comma, I can call this the retarded time, but it is t minus r over c minus r hat dotted with, right, significantly similar. That's it. So in the radiation zone, so in the regions very far away from the sources, that's called the radiation zone. 1 over r potential is the only thing that survives, and and the coefficient is given by an integral over the sources, right, with this retardation that comes into picture. So there is a first main retardation is because of the distance r itself, and there is a orientation also plays a role because r dotted with r prime. So there is a small feature in there, and this is often called t retarded, right? This is t retarded. So, okay. Same thing goes through for the vector potential also. Let me write that down. This is mu naught over 4 pi. Again, 1 over r comes out. It was the same expression, except now you integrate over the current density. In fact, here this time I will write T of r, right? T of r, as understood that it is the complete entity inside and there. There is a there is a distance r in there, so that is important, and vector orientation r hat also shows up there. Okay, that's our expression, and we will try to keep this as general as possible, very generic. Notice any charge distribution we are talking about, but came at a very extreme limit that we are in the only in the very far away zone. It's like saying we are sitting on Earth, and when you look at the sky, that's at infinity, right? So think of a spherical region all around you, but at infinity. So all the distances are gone. So it's only the 1 over r potential that will be there. Intermediate distances do not come in, but orientations are important, and that's what we will work with. Okay, that's the idea. So these are your fields. So this will be called the radiation fields or radiation potentials, right? So this is radiation potentials. Once you have the potentials, we can find the electric and magnetic field, right? So in the rest of the 2 weeks, we will always start from these 2 points, right? In the radiation regime, the potentials are given by this expression, and then what can we do with that? Okay. Any questions? Right. Okay. Okay. To calculate the electric field, we simply have to take the negative gradient of the electric potential and the time derivative of the vector potential, correct? We have the potentials now in the far field regime. We just have to do this. That's del cross A. Okay, so that will be our exercise, and let's begin with the gradient of the phi there. So let me write down this phi expression again. So phi of r of t is equal to 1 over 4 pi epsilon naught. It sits there all the time. 1 over r, and there is an integral t cube r prime of rho of r prime. We don't care for r prime, and there is t of r. And what is this retarded time? T of r is equal to t minus r over c, observed magnitude of that quantity, and that is minus oh, I messed up, right? Oh, I messed up a little. So if you notice, one board back, I did r minus r prime. These were the two factors. When I substitute it in, this will become a plus sign. Agreed? This was t minus the magnitude r minus r prime over c. So this will become a plus sign there. And that's a plus sign. And t of r accordingly changes. Okay, sorry about that. So now this is t of r hat dotted with r prime over c. Okay. Now if I'm taking the gradient, so I'm interested in the negative gradient, but let's talk about gradient of phi. How will it work? It is going to hit everywhere there is an r, correct? And where are the places it sees the r? It will hit this r, correct? And it will also hit wherever there is an r inside of the retarded time. So it will hit here and here, right? Two places. So I need to learn how to find the gradient of 1 over r, which we already know. We have used that a lot. That's the electric field. And we want to find the gradient of this retarded time, and that will be the new thing. So this is equal to 1 over 4 pi epsilon naught gradient of 1 over r. That's easy. That's basically the electric field up to a sign. No, I think that's the electric field exactly, right? 1 over 4 pi epsilon r electric potential, and then no, negative of that is electric field. And this remains as it is, t cube r prime rho dr, but I can also hit the retarded time. So let me write that down. So plus 1 over 4 pi epsilon naught 1 over r, and and I have to hit tr that is appearing inside. For that I use a chain rule, right? So I will take the derivative with respect to the argument of the retarded time, and then take the gradient, right? So first let me take the gradient. So this is a chain rule I'm doing. So this is a gradient of t of r, right? So let me close that in brackets, and then I have to take the derivative of the charge density with respect to its argument, which is t of r, right? Which I can take it as derivative with t, which will be the same. So this will be d by dt of rho of r prime comma t. But then I have to replace this whole thing with t equal to t of r. That's one way of writing it. Otherwise, I could have written this as derivative with T of R, and that's T of R. That's the same thing. So I want to write it like that so that later on, if we want to use some conservation principles, then we can use that. So if I want to evaluate this, I have to do two things. One is gradient of 1 over R, which we know is like calculating the electric field, and the gradient of T of R. So first, let me immediately write what is gradient of 1 over R, right? That's the immediate one. So that's minus R hat over R square, right? That's the idea of electric field. Like we have done this many times. So we do it coordinate independent way. No, we don't have to take the derivatives explicitly. Next, we want to calculate what is the gradient of T of R, right? That's the retarded time. And let me move the board space. And that's the same as gradient of what is T of R. So there is T minus R over C and plus, let me write that as R hat over R, right? So this is R hat, oh sorry, R vector R over R dotted with R prime over C. Right, that's the gradient does not depend on the time. That's not there. What's the gradient of the magnitude of R? What's the gradient of the magnitude of the position vector?
R vector?
R hat, right?
R
Not
hat.
R vector. Because it cannot have dimensions, right? So gradient of R will be R hat, right? So this is 1 over R, so it's a dimensionless quantity, so it's R hat, right? So that's what it is. So this is equal to, it hits on this to give you minus R hat over C, correct? That's R, not gamma, okay? And now I can hit two places, correct? Either a numerator or the denominator. When it hits the numerator, right, it is gradient of R. Remember, gradient of the vector R is equal to the dyadic, right? Which is going to get multiplied by R hat. So that's the gradient over R minus of R hat, oh, sorry, R prime over C. That's when it hits the numerator. When it hits the denominator, it's like your minus R hat over R square, right? So this is minus so of that, and there is a negative of that. So this is now so this is negative R hat over R square, and there is a vector R dotted with R prime over C. Hopefully all these dimensions are correct. Let's see if I got all the dimensions right. It doesn't seem like, yeah, it seems like. So this is 1 over C. That's also 1 over C. There are two R's, so that's also 1 over C, correct? So just let me simplify this a little. So this is minus R hat over C. This is plus R prime over R. That is 1 over C, right? And here it is R square. So that is minus R hat dotted with R prime and sorry, R hat times R hat dotted with R prime over R, right? And then there is 1 over C. And notice it is not higher order. If it is higher order, I can delete it, or I can neglect it, because already I have dropped a lot of higher order terms. But this is 1 over r here, magnitude like in the dimensionless quantity, and this is also 1 over r, except the orientation comes into a picture. So we have to keep all those terms. Okay, from that, so now I can substitute those things. So let me see if I have until now. But this can be simplified. So that's one nice thing about this. Let's see. The whatever we have there can be expressed in a slightly different way. Notice that this is equal to minus r hat over c minus of, let me put this in here, and let's see, 1 over c, and let me put it this way, r hat crossed with r hat crossed with r prime over r. Okay. Notice that the second and third terms are nothing but can be put together using your back-cab rule. The back term, the r hat term, is this. This is the direction r hat, and these two are dotted. And the next one is r hat dotted with r hat, that gives you a 1, and it is r prime over r. So that's one way of writing it. That is crucial, actually. Later on, it will play an important role because it will turn out that radiation fields are always perpendicular. Electric field will always come out to be perpendicular to the magnetic field. Radiation field in every sense, it satisfies all the criteria for a plane wave. What are the criteria for a plane wave? Do you guys remember what are the criteria for a plane wave? A plane wave is what we think of as an electromagnetic wave of a single color, and it goes infinitely forever, starts from minus infinity and goes to plus infinity. There is a direction associated with it, k. So there's a direction associated with it, k hat. Let's say electric field could be perpendicular to that, and magnetic field will be coming out of the board, right? E cross B will always be in the direction of propagation of the wave. More importantly, the energy stored in the electric field will be exactly the same as the electric energy stored in the magnetic field, always, like irrespective of what time it is, always the energy stored in the electric field is exactly equal to the energy stored in the magnetic field. And then momentum is in the direction of k vector, and there is one more. What is that? And that is a flux of energy is given in the direction of k. So those are the information in the Maxwell's equation, if you want, for a plane wave. And the radiation fields, even though we haven't shown it as of now, it will turn out that this very far region or electric and magnetic fields in the very far regions from sources moving in time will always satisfy these properties of a plane wave. So conceptually, that plays an important role. So if I were to take this in and substitute it in there, so let's see what comes about. So let me so now that I know the gradient of the retarded time and the gradient of 1 over r, I can write down the gradient of the electric potential and moving the board space. So gradient of phi is equal to minus r hat over r square. Let me write that down. So it's 1 over 4 pi epsilon naught, and that is, there's a minus sign, so there's minus of that, and that is r hat over r square. This is T of r. Right, that's the first term. Oops. And the second term is gets distributed from two pieces, right? So that is, let me write that down. So that's minus, so this minus 1 over 4 pi epsilon naught. You might have to look into the previous expression since it's not on the board available to you guys for seeing, and that is minus r hat over c. Right? So this is minus r hat over r, and that is a factor of c, 1 over c, d cube r prime. Let me put the c inside. So that is d by dt and 1 over c and rho of r prime t, and the whole thing is evaluated at t is equal to the retarded time. Right? That's the first term for the gradient of the retarded time that contributes, and the second term is minus again 1 over 4 pi epsilon naught, and there's this cross product showing up, right? And yeah, there is a 1 over r already in there, right? So the way to write this would be, so minus 1 over r times r hat crossed with r prime over r, and the whole thing. Okay, with me. So this is the gradient of 1 over r. This is the gradient of the retarded time, the first term from there. This is the gradient of the retarded time, second term from there. Okay, but now comes the radiation regime approximation again. We are only interested in the leading order. We have thrown away a lot of higher order terms already. So what's the point in keeping extra terms, because it will be error prone. So this is 1 over r square, and this is 1 over r, and this is 1 over r square. Right? This is higher order relative to this. This is higher order relative to this. Right? So this is 1 over r square. This is 1 over r, and that's 1 over r square. Doesn't matter what it is, I have to drop 1 over r square because already I have dropped a lot of them. So these are error prone. So I cannot keep the higher order terms and expect to get anything meaningful out of it. So in the radiation approximation, those two are not there. It's just this. So this is minus r hat, and this is 1 over 4 pi epsilon naught, 1 over r, and that is all there is to it. Okay, so let me. So the power of extreme approximation, almost everything gets too simple, right? There's a just charge, I mean, integrate over all the charge densities is like saying total charge will be captured, except that all the retarded times, like if there is motion here, It's the motion at the retarded time, like you have to fix the charges at the retarded time, that is important. Like that is the only catch here. Otherwise, it's just 1 over r potential. Like it's like statics, except charges are all in the retarded regime. That's your gradient of phi. If I had started with negative gradient of phi, which is what is there in the electric field, I have to switch signs. That's negative, positive, positive, and this would have been a positive sign. Fine. Correct. And it's in the radial direction. So from the source, go in the radial direction, and radiation field is always in the radial direction. Is that correct? No, it is not completely in the radial direction, because this is only gradient of phi, right? There is also a piece in there. So that's also going to contribute, and that will change it. So electric field is usually not in the radial direction, it's perpendicular to that. We'll see how it comes about. Let's make me sure that's indeed the case. Yes, so as of now, this is perfectly fine. Okay, so the same thing we can do with dA by dt also, right? So let's calculate the other two terms. So first, let me do del cross A, right? So there is a del cross A, and then I have to do the time derivative also. So, but while I'm doing the gradient, it is easier to look at the curl also. It will be the same result, except that I have to take the curl into picture. So here, instead of r hat multiplying with this will be a current density, and there will be a cross product that will show up. So this will be equal to, if you want, so that's equal to mu naught over 4 pi. So let me write that as mu naught over 4 pi. And then there will be 1 over r. So let me write it as r hat over r crossed with, this will become current density. This is d cube r prime, and 1 over c d by dt of the current density. Okay, with me? So pretty much the same idea, because it's all the expressions were exactly the same. So let me make sure I have everything there, and we also need the time piece there, right? Okay, so we're almost there. Correct. Any questions at this stage? These intermediate steps hopefully are all clear. And the time derivative with respect to A will be time appears only at one place, so it is just the time itself, right? So so that's equal to mu naught over 4 pi, and then there is 1 over r and d cube r prime. And I have to now write, so I'm thinking whether to write the c or not. So there is no c, so this is the time, so the dimensions of this are different, correct? So this is d by dt. If you want, I can write the 1 over c here and multiply the c somewhere here. R prime, and this is t of r. So this is hitting only the time piece in there. Okay, and in principle, I don't have to put in this c, so let me keep it as it is. Okay, good. And now electric field is pretty much putting this all together, right? Let's begin with the magnetic field is the straightforward quantity. That's just this piece dotted with that. And what is the electric field? So electric field is, am I in the board space? Yes, as of now. That's equal to gradient of phi minus of dA by dt. Okay. Just putting this together, I have to add this and this, right, R plus that piece, and we will see that this is actually a cross product. But we will do that in a minute. Any questions before that? I'll put this all together in a minute. Okay. So there's only one catch in here, that there is a time derivative here acting on T of R, and here it is a time derivative. This is all T of R itself. So that's the only small caveat there. Otherwise, we have all the ingredients that will bring it all together. Okay. Any questions? Okay. So yep. Okay. Let me see how I want to proceed. So that's a magnetic field. Give me a second. Yeah. Okay, so there's a slight complication here, I'm thinking, but let me write down the first easier part first. Okay? So we have to work this out, right? So let me leave that alone, but let me write down the simpler answer first. In the board space now. So let me write down the simpler answer first, and that's the magnetic field is equal to simply this, right? Del cross A is magnetic field. So it is R crossed with this whole thing here, right? So yeah, so how do I want to write it? R hat crossed with, how about that? So this is R hat crossed with mu naught over 4 pi times 1 over R, and this is an expression we will, like, our final answer will be in terms of this. So that's what we are going to keep, and this is 1 over C d by dt of J remember the retarded time, so this has to be evaluated, and that will be our magnetic field. This is the final answer. So if we want the radiation contribution to the magnetic field is 1 over R, we just have to evaluate the time derivative of the current. Remember, current itself is having a contribution. It's like a velocity. So time derivative of current is like an acceleration, and that's where that acceleration shows up. And we have to do everything in the retarded regime. Like we have to put that in the retarded regime. Electric field, let's process this. It requires a little more work. Okay, so electric field is, if I were to just collect the terms, electric field is negative gradient of phi, that's this expression, and negative gradient of A is this expression, I suppose. And let me see that. And yeah, where is this? Yeah, so this is equal to R hat 1 over 4 pi epsilon naught times 1 over R and d cube R prime, and that is 1 over C d by dt of rho. Evaluated at the retarded time. Right, that's the first term, and that comes with a negative sign actually, because it's a negative gradient. Oh no, I already took care of it. Sorry, so that's positive sign because I already took care of it. And then there's a negative mu naught over 4 pi. So this is negative mu naught over 4 pi. This is 1 over R and d cube prime and d by dt of j. Right, this is evaluated at the normal time. No, this is T of R, sorry. This was T of R. I think, yeah, I did write it correct there. Yeah, this is T of R. Okay, so how do we proceed to evaluate this? We will process the first term. Remember our current conservation equation, right? D rho over dt plus gradient of J is equal to 0. Correct? So that was the current conservation equation. And this is in terms of current, that's in terms of charge density. We can process this further so that we can write everything in terms of the current conservation. Okay, so that's the idea. Replace this in there. That comes with the negative sign. So this is electric field. Or let me do one thing at this at one time, right? So instead of the electric field itself, let me just process this expression in there. So if I were to have d rho over r prime t over d by dt evaluated at t equal to t of r, that's the same as, I can replace this with negative gradient, but this time it will be r prime, right? So it will be negative gradient of prime, and that is a row of, sorry, j, right? So j dotted with j of, this is evaluated at the same time. So this is of r comma t. Agreed? So that's just using the, this is R prime. This is simply using the conservation principle. But I would like to release this t equal to TR. So let's do the following. Remember that T of R, so I'm going to write that, squeeze that in here. So T of R was nothing but T minus R over C plus R hat dotted with R prime over C. Right? There is only one place that R prime shows up, and that's there. Right? And so I'm hitting with prime here, and this is acting only on R prime here. If I were to evaluate it at T equal to TR, that's different because I'm putting it at a later stage. So this is equal to negative gradient dotted with J of R prime comma T of R. That's not completely correct, but because now this is hitting at two places. This is hitting at R prime here, and it is hitting at the R prime inside the retarded time. That's not correct. So I want to accommodate for that by removing whatever we get if I hit on the T of R. So that is equal to plus, right? This time I'm going to encounter whatever that time derivative is. So this will be hitting your gradient in here. So that's equal to 1. So that's R hat over C, right? Whatever I get from there, and the time derivative. So this is d by dt of J. J of t evaluated. This is a chain rule again, right? So that's your t equal to T of R. Right? Again, what have I done here is that this is evaluating the derivative and then substituting T of R. Instead, I directly substituted T of R, but that's not correct because if I do that, this gradient gets to hit at two places. But instead of correcting that, I correct that by adding whatever term is the extra piece in there, right? That's the idea. Okay. Is that clear? Any questions on that? Okay. And then what do I do? Let me make sure I'm thinking correct here. I want to follow this. So let me. So, oh, there is a. Oh, I missed that. There is a dot product, right? So since this is a scalar, that should also be a scalar. That's a dot product there. Right? That's immediate. So that's a dot product there, and that's correct. Okay. So that seems to be correct. But now we have an integral in there, and we just have to carry it over. Yeah, and then we can apparently collect this all together in a nice way. Okay, so substitute this back in here. I have to do an integral. So integral of d cube r prime evaluated at r prime t and t equal to tr. When I integrate it, I have to integrate over this dot of j. When I integrate that, that's equivalent to doing a surface integral of dA dotted with j, right? On the surface of the, so this is on the surface of the universe or in the radiations regime. And that is plus r hat over c dotted with d cube r prime and with the time derivative. same as earlier, t equal to t of r. Okay, with me? We are talking about a source, we are talking about sources confined in a certain regime, in a very confined region. We are not spreading it out all over. So this is pretty much zero. The sources are all confined in a small region, and in the radiation zone, we don't have any sources. That's a premise of the radiation zone. So this is equal to zero. So this has suddenly become, so what we have practically done is that we have written our time derivative with charge of charge density as time derivative of current density, and both evaluated at t equal to tr, and it seems like that should be unreasonable, but it is because of this current conservation that that's possible, right? So what's our electric field? So let me put this all together. So electric field, if I were to substitute this in, there is already an r hat there. So I have 1 over 4 pi epsilon naught, 1 over r hat. So I will put that in all together there. So this is r hat vector, and then there is r hat dotted with 1 over r, or actually I should put the 1 over 4 pi epsilon also in with it. Maybe that will be much more easier to see through. So this is vector r hat, then r hat dotted with 1 over 4 pi epsilon naught, 1 over r, and then integral. And now the integral is the same as what appeared earlier, right? 1 over c d by dt of j, right? And there is a c, everything is there, yes, right? J of r t, and this is evaluated at t equal to t of r, right? That's the first piece, and the second piece stays as it is, and this is equal to minus mu naught over 4 pi, and there is, let me put a c there, so mu naught c, and then there is 1 over r. I think I'm missing a dimension here. Help me out with that. So this is 1 over r d cube r prime. That is 1 over c again, d by dt. Right. Both have pretty much the same, except there is an epsilon naught here and there is a mu naught c. So I think there should be a c square here, because then I will get the epsilon in there, right? Why did I miss a c square there? Help. Oh, because there was an extra c. No, that c that goes into there. That was okay. Yeah, this has an extra c here, right? Because there is d rho by dt, rho, and no, that's okay. J and c cancel out, right? Yeah, so that's okay. That's okay. Why am I missing a c? Help. Oh, I can look into my notes. Let's see. So that's correct. Yeah, this seems to have an extra C in here. And why was that? To begin with, goes all the way back. Can you guys see any extra C here? Okay, let me check my expressions for the earlier case. You guys agree that there is a dimensional error here, right? Right, these two are exactly the same, except for there is a C. Like if I were having C square here, then that is a problem. Okay. Okay, check. Why am I not able to see this? Okay, let's go back. I know I've crossed my time, but I think we are almost in the last two steps. I don't want to stop here because then we'll have to take all this, we'll have to review, okay? So I'll take maybe 5 or not more than 10 minutes, okay? But let me fix this. Okay. Oh yeah, I see it. That's almost right there. Notice that if I were to go one place up, there is a C here, right? That's one C. And the time derivative, the integral of the time derivative, which I think is in this expression here, right? That has a C in here. If I introduce that C here on the left hand side, that will be a C square on the right hand side. Agreed? Here there is a C. If I were to put that in here, so that is, if I were to put a C there, which is what is there in the integral, so 1 over C, that will be make the C square. And that's exactly the C we need. So there's no error at all. It's just that I was not counting it correctly. Okay. So electric field here, so this will be C square, right? So there is a C square there. So let me write that all the way down here. So this is C square. So let me pull that C all the way out, and this is 1 over C square. And we don't need the C here. So that's a better way of writing. So then I can write everything in terms of mu naught over 4 pi. C square is mu naught epsilon on top. So epsilon cancels out. So it's the same mu naught over 4 pi that shows up there. But now this has this nice feature that this is again a cross product, right? R dotted with. So there is a R hat vector, and there is R cross R hat. So what this is equal to is, let me, so this is the same as, so mu naught over 4 pi. Right, so this is so this is R hat crossed with R hat crossed with whatever we have. So this is mu naught over 4 pi 1 over R and d cube R prime. Great, and the things close there. Okay, that's your expression, but this is looks little. Let me summarize this, and it looks very nice. But let me confirm that
Can
before.
you move the board a little bit down?
Oh,
the last expression is not
Oh,
visible.
sorry. Very sorry. Okay, very sorry. So what I did was, there is this R hat and this minus. So this is basically a back cab rule. If this whole integral can be interpreted as a vector, this is pretty much a back cab rule. Let's verify that. This is R hat dotted with this quantity. That's what this is. And this dotted with this is 1. And we get whatever is there inside the inside the integral. Okay. With me? So what we have altogether is what was the except let me go back again, a tiny error, right? I did gradient of phi and showed that this is a positive R hat, correct? And then the curl of A, I almost copied this down saying that, oh, there will be a cross in between. But this is negative gradient, so this will have a negative sign. So there is a negative sign in there. Okay, that's because this gradient was operated for negative gradient that gives you positive. So it's a positive curl that will give you a negative sign here. So the magnetic field has a negative sign in here. Okay, so let me summarize all this together. So this is the key piece, which is what we will use. So overall, what are the fields in the radiation regime? So we have magnetic field, which is having a C there. So let me write this as C times B. Okay, I pull out the magnetic C from the right hand side to the left hand side, and that's equal to minus R hat crossed with. So let's actually introduce a new term. Maybe that is a good thing to have. Let's say J effective. Okay. Let's call something as J effective. Is equal to oh, but then there is a time derivative and all comes in. Now let's just write it as it is. Yeah, okay, sorry. So I might have to define the right term for that. Minus R hat crossed with mu naught over 4 pi 1 over R and integrate. These are going to be relatively easy integrals. We will see applications next time. This will be very simple. Or relatively simple. T is equal to T of R. That's your magnetic field that we did a little while ago. And the electric field, if you notice, doesn't need any extra work. Like electric field had the magnetic field inside. So this is equal to minus R hat crossed with your magnetic field. Oh, sorry, C, C times B. That's it. So it's a relatively simple expression. So if we can do that integral, we are all good. So as a minus CB, yes, everything is fine. And to the leading order, of course, this is plus higher terms are there, but we are not keeping that in the radiation regime, right? So there is a leading contribution in there. So again, if you notice what is happening here, just to give you an interpretation. So these are sources here, and all the way out at infinity. So there's a sphere around that source that can be formed. And this is your R hat, right? And an arbitrary direction, that's your R hat. Go very far in the far field limit. The electric field, first let's get the magnetic field. This is R crossed with whatever is the direction of your J. So J decides that, not even J, it's a time derivative of J that decides that. So let's say the magnetic field is surely perpendicular to that, right? So there will be a magnetic field, let's say, is in this direction. That's your B. And B crossed with R, and then you put a negative sign, that's your E crossed B, right? So this is your E. That's your E. So electric field and magnetic field are tangents to the sphere in the far field, and they are both perpendicular to the radial vector that's projecting outward at every point, of course. And that puts a lot of constraints, topological constraints, right? I mean, these field lines have to close with each other, so that puts in a lot of constraints in there. And those are nice properties, and that is what is the antenna or radio electromagnetic fields in the antenna region. They have this nice patterns that they form. That's because it is topologically constraint, just that there should be no sources for either one of them. And this is going to, so the primary expressions we'll begin with next time is electric field and magnetic field given using this. And the prescription is find J sources and take the time derivatives, and that gives you the electric and magnetic field. So that's how antenna works. For a simple antenna, I shouldn't say technologically these days we have very sophisticated antennas. They do a lot of things. They use material properties to do various things, but this is the simple, we'll call it a simple antenna, and this is how it works. Okay, sorry about searching for that speed of light, C in between, otherwise maybe I would have been a little better in time. But this really helps. I think now we are 2 weeks, we might be able to catch up with sufficient stuff. Okay. Like otherwise this would have been spread out into 2 lectures. So putting this in 1 lecture really helps, and that too in an extra lecture. Thank you. Any questions or comments? So the main idea was just to get the radiation fields, and it is much simpler. Okay, thank you.
All right. Bye.
Yeah, bye-bye, and have a good weekend.
All right. Thanks, Josh. You do the same.
Bye-bye. Yeah, have a good weekend. Yeah.